This topic we explore is inspired by Feynman, Volume I, Chapter 20. We attempt to explain rotation in 3 dimensions in our own words while retaining the essence of Feynman's original lectures. We begin with a wheel, rotating freely in space, simple to observe, but complex mathematically. Rotations exist not just in a plane, but across all 3 axes. 2-dimensional torque rules still apply in general. Xe Planck equals rate of change of angular momentum x by my epx, representing motion about z-axis. Other planes behave similarly. I's plane has torque, Vf's my zfi, angular momentum yc nide c, zx plane torque is, zfx max xf's, angular momentum zpx max p's. When multiple particles combine, angular momentum adds, torque sums over planes, law generalizes naturally, no new independent torque. Some may ask, what about arbitrary planes? Feynman shows clearly, any plane's torque is combination of 3 principal planes. Nothing fundamentally new, only mixtures of c, y's, zx. Next, consider rotated axes. Joe uses cis coordinates, Mo chooses x, y's. Suppose only x axes are rotated by a z-axis remains unchanged. Torques can be vectors, initially planar scalars, transform like vectors with proper analysis. X cos pla y sen. Y max x sen sa y cos, z tub z force components transform similarly, fx cern fx cos phi phi sine, f hi my fx sen fluff I cos f z as z. After substitution algebra, xi su torque simplifies, ta xi pal x y, rotation in plane unchanged, magnitude remains the same. New planes yz and zcx have torque transformed. Toys das toyes cos ta tau zx sin, bazek si pao tau zx cos ma tau z sint. We associate components as vector representation, pa zitan toxi I tau x tan toyes plau I pa zx. Torque acts perpendicular to the plane of twist. Magnitude represents strength. Right hand rule defines direction consistently. This property exists only in 3 dimensions. 2-dimensional torque, scalar remains, no vector required. Cross product arises, sika ta b, perpendicular to a b, magnitude a b sinc, direction follows right hand screw. Cross product is anti-commutative, b tau a tamau e tau b, a tau a tau 0. If vectors, I-packed notation applies torque, momentum, velocity, ta parataf el partala p, ta tadls dt, ta xt dltot dt. Conservation of angular momentum follows immediately. If ta x to 0, lot remains constant. Angular velocity L vectorial represents combined plane rotations. Parallelogram rule applies, magnitude determines speed, direction determines plane. Power from torque, pia pama, applies in 3 dimensions. Rigid body velocity, v talgan r, Coriolis force, fc to 2 men finau, appears in rotating systems. Cross products unify rotation descriptions elegantly. Gyroscope illustrates principles, swivel chair, spinning wheel, axis horizontal initially, angular momentum horizontal. Rotate wheel vertical, forces act on system. Chair rotates opposite spin, angular momentum conserved. Torque arises from hands, applied to change wheel axis. Newton's third law applies, equal and opposite reactions. Wheel, chair, operator, form, isolated system, vertical momentum conserved. Precession observed naturally, rotation direction perpendicular to applied torque. Now let us examine the law of conservation applied to spinning wheels or gyroscopes in action. Imagine sitting carefully on a frictionless swivel chair, holding a spinning wheel, axis initially horizontal, angular momentum horizontal. If we rotate wheel, axis toward vertical slowly, angular momentum vector changes, direction shifts, magnitude constant. Torque required is time rate of change. Tato 0 elda jarntitelo 0. Forces applied at axle ends cause equal opposite reaction, rotating chair opposite direction. This behavior is surprising, yet perfectly consistent with Newton's laws and the conservation principle. Consider a rapidly spinning wheel with angular velocity, nigh along y-axis, small tilt along x-axis, angular momentum mostly along y. As wheel precesses slowly, particles on rim move, not in simple plane. Paths become curved slightly, lateral forces required, transmitted through the wheel spokes. Balanced forces produce smooth precession, uniform motion. Torque from gravity or hands translates into circular rotation, axis traces conical path, precession perpendicular to torque. Nutation occurs naturally, superimposed wobbling, oscillations, axis tip traces complex path, quick motion damped rapidly, settling into steady precession. Observing slowly spinning wheel, nutation becomes obvious, axis overshoots average plane. Cycloidal tip motion emerges, friction gradually reduces oscillation, steady precessional motion achieved. Gyroscope experiments demonstrate torque, angular momentum connection, mathematical rules appear miraculous, yet explainable. Angular momentum vector may not align with angular velocity, especially in irregular bodies, lopsidedly mounted wheel, axis through center of mass. Rotation generates centrifugal forces, plane aligns perpendicular to axis, bearings resist, torque exerted, rate of change angular momentum. Components vary by axis. Principal axis concept arises, 3 perpendicular axes, through center of mass, maximal, minimal, intermediate inertia. Rotation about principal axis aligns angular momentum with Ehlers symmetry axis. Simplify analysis, rigid bodies obey predictable rules. Moments of inertia along axes, denoted A, B, C, angular momentum components, Elta ni xi slabina y j sino zik, rotational kinetic energy expressed, Ke pun 1 dungeoner 2 or equivalently, Km1 under 2 ou. Now let us analyze forces acting during precession. Particles move in curves, spokes transmit lateral forces, equal and opposite on both sides. Wheel can sustain torque. Due to gravity or applied forces, precession continues smoothly. Uniform motion achieved mathematically. Yet intuitive understanding requires physical reasoning about forces, accelerations, and particle motion. If torque suddenly removed, gyroscope does not simply fall. Sidewise motion emerges, direction dictated by prior angular momentum, steady precessional component remains. Initial drop causes oscillation. Overshoot of axis occurs, path of tip resembles cycloid, damps rapidly through friction, final steady precession emerges, axis slightly lower than start. Slow wheel rotation, more pronounced nutation observed, rapid spinning minimizes wobbling, precession dominates motion, axis stabilizes dynamically. Torque application and reaction. Illustrate right. Hand rule. Forces at axle translate into system rotation oppositely. Conservation of vertical angular momentum explains swivel chair motion. Mathematical relations confirm. Totalope IL0 applies to tops, gyroscopes, any spinning rigid body, precessional motion perpendicular to applied torque direction. We can visualize vectors, angular velocity, EBJ, and momentum L. Pseudo vectors emerge naturally, polar ves, axial vectors clarified, torque, angular momentum classified, magnetic field and UBI. Examples. Cross products simplify representation, topar ra tau f, ulpar r tau p, angular velocity decomposition, parallelogram rule applies, magnitude indicates speed, direction determines rotation plane. Precession rates predictable. Angular momentum vector change. Small tilts produce lateral forces. Force transmitted through wheel. Spokes carry stress efficiently. Rigid bodies with asymmetry. Principal axis analysis essential. Torques aligned. Angular momentum predictable. rotation controlled physically, not purely mathematically. Gyroscopic systems demonstrate how forces, rotations interconnect, precession, nutation, torque, vector relationships crucial, engineering applications, navigation, physics, emphasize Feynman's insightful approach. Let us continue now with more subtle rotations, three-dimensional rigid bodies, and angular momentum effects. First, remember principal axes, maximal, minimal, intermediate inertia. Any rotation along these axes aligns angular momentum with EBU, simplifying analysis greatly. Consider a lopsided wheel, axis through center of mass, rotating rapidly about axis. Angular momentum vector not aligned, torques applied through bearings, necessary to control rotation. Components of W along axis, denoted WX, Ni uz, moments of inertia A, B, C. Angular momentum Elton A no excitlobia Y J C no ZK, energy Ke 1 by 2 Eldenman. Now visualize a gyroscope rapidly spinning in horizontal plane, pivot frictionless, torque free initially, axis tilts slightly, precession begins, forces applied at axle ends, accelerations transmitted through wheel. Particles move along curved paths. Net force 0, but torque exists, side to side forces balance. Precession occurs perpendicular to applied torque, consistent direction. Nutation emerges naturally, axis oscillates about average orientation. Cycloidal tip motion appears, friction damps oscillations quickly, leaving steady precession dominant, axis slightly lower than starting point. Torque and precession vectors obey right, hand screw convention, direction of angular momentum, perpendicular to plane of torque, length proportional to twist magnitude, pseudo, vector properties confirmed. This behavior generalizes for spinning tops, gyroscopes, any rigid body with spin, angular velocity vector decomposed, along three principal planes, parallel projections combine geometrically. Vector sum gives net rotation. Physical intuition clarifies mathematics. Particles in spinning wheels, accelerations produce lateral forces. Transmitted through solid structure, torque applied through hands or pivot produces opposite reaction. Rotation of supporting system, conserving total angular momentum. We can now formalize vector product rules, cross products, tapa rat F, laka rata P, of vector projections along planes, magnitude and direction determined, power calculated as P top tonduen. Angular velocity magnitude multiplies torque, producing work at that rate. Rigid bodies with symmetry, simpler analysis possible, principal axes coincide with symmetry. Angular momentum vectors predictable, rotational energy calculated easily, even irregular objects follow rules, requires decomposition along axes. Gyroscope motion, precession, nutation, all explained mathematically, yet physical reasoning crucial. Visualize particle motion, forces, torque, path of axis, tip understood, cycloidal, damped, settles into average plane, ensuring conservation laws obeyed. Torque, free rotation remains simple, L constant, Elbame wobble, nutation appears without external torque, precession emerges if torque applied, vector analysis predicts orientation changes, magnitude, direction of L determined, multiple axes rotation combined results. In new effective axis, angular velocity vector sum, parallelogram rule yields magnitude. Plane of rotation emerges naturally, consistent with experimental observation. 3-dimensional rotations inherently complex, yet cross-product formalism, vector rules, and pseudo-vectors allow compact representation. All physical behaviors described, conservation of angular momentum obeyed, precession and torque linked precisely. Gyroscopic phenomena are remarkable, not mystical, but explainable using classical mechanics carefully. Mathematics provides predictive framework. Physical intuition ensures understanding. Feynman's approach emphasizes clarity, concepts made accessible to students. Finally, remember, in 3D, angular momentum not always aligned. Principal axes simplify understanding. Moments of inertia dictate behavior. Torque application produces predictable motion. Precession, nutation, rotations fully described. For engineering applications, navigation, physics, gyroscope, behavior critical, vector formalism. Cross products, essential, torque, angular velocity, angular momentum, interconnected. Provide complete description. Rotation in space, no longer mysterious. Feynman's insights guide careful analysis. Thus we conclude our study of three-dimensional rotation. From angular momentum basics, torque vectors, cross products, gyroscope precession, nutation, to principal axes of rigid bodies. Physics of spinning bodies, mathematically rigorous, physically intuitive, illustrates beauty of mechanics, how simple laws produce complex effects, all derivable from Newton's principles. Feynman's lectures reveal understanding, making advanced physics approachable, even for those new to the topic.